Okay, this week we're going to start talking about pressures. Uh, a lot of you know, you not realize you actually have a lot of weight on you every minute of every day because of the atmosphere. The atmosphere has a weight, and that's all that air that is above you weighs something. So, what is the significance of this weight? How does it vary, and how is it important in forecasting the weather and what's going to happen? So, what is this first off? Weight is basically a force, which is mass times acceleration. So mass, how many molecules do you got in one area? That's kind of a mass. The heavier these molecules are, the more that air in that segment weighs. Acceleration is just like you putting your foot on the gas pedal in your car and starting to go faster. That's an acceleration. So these two together equal a force, and basically a force is what air pressure weighs. And one of the key factors of that on Earth is a force is always gravitation, pulling the air down towards the Earth. So that is why we have weight on us. Dalton's law basically just says, hey, each one of these gases has a weight. When you combine them all together, that's what the air mass weighs. And that is true. Now, with this kinetic energy, the mass of molecules in kinetic molecular area, so weight is basically the force of gravity exerted on a mass. The less mass, the less weight. So we're going to look at that, why that changes within the atmosphere. Here is the way we measure. We use a barometer. We used to use mercury barometers. We don't anymore. Basically because mercury barometers are dangerous. So most of them are aneroid barometers now. They measure in inches of mercury or in millibars or in other units. Each one of these units can be related to each other. And here you see a whole list of units there. So air is compressible. What does that mean? Have you ever tried to compress water? If you push it together with your hands, it just kind of squirts out. Well, air, on the other hand, is compressible. In other words, there is more air molecules down near the surface than there are further up in the atmosphere. The air that was at the top of the atmosphere has pushed them down, so there's more of them here. That's why the highest pressure is the lowest in the lowest section of the atmosphere. So there's going to be a drop in pressure with altitude as you go up, because there's going to be less molecules there. Here is looking at how pressure changes over time. So pressure is going to change when low pressure moves by, the pressure is going to drop. High pressure moves in, pressure is going to rise. This is a basic mediogram. You're going to see this in your workbook this week in your investigations. All it is temperature is plotted along time is plotted along the bottom, and some other variable is plotted on the y-axis. So in other words, all you're doing, if you wanted to know a pressure at a certain moment in time, you find that moment in time and look up, there's your pressure. So rising air temperatures, there's an increase in kinetic molecular activity. If you heat the air, and air is not in a closed container, so what's going to happen? That air is going to tend to push the molecules further apart. That means the air is going to weigh less. So the more kinetic energy, the less the molecules you're going to have, and the less density that air mass is going to have. So typically you would think that, a lighter air, because it weighs less because of the temperature increase, is going to have less density and less weight. The pressure is going to be lower. And sometimes that's definitely part of it. But unfortunately, that's not all of it. So with that being said, in a very cold air mass, the air temperature is going to drop very quickly because you have a whole bunch of molecules packed together. So if you go up in a vertical, the pressure is going to fall very, very fast. That is why when you look at low pressures aloft, they're going to be centered over a cold air mass because the pressure has dropped faster. Now, when you have the opposite, hot air, like we've had in Texas this last week, what happens is the pressure drops slower with height, and you wind up with higher pressure above Texas, in this case, wind up with high pressure aloft. So there is a correlation. When you see low pressure aloft, you're going to have colder air. When you see high pressure aloft, you're going to have warmer air. And guess what? As much as we think air is really, really heavy when it's very muggy, it's actually lighter. When you add moisture, the more moisture you add to the air, it actually is less dense than the current air without moisture. So cold, dry air masses are going to weigh a lot more than a cold, wet air mass, for example, or a warm, humid air mass, like in the summertime, is actually going to weigh significantly less. So with all of that, another factor that influences pressure, obviously, are winds. So if you have winds blowing together aloft, that air's got to have somewhere to go. So where's it going to go? It's going to get pushed down to the ground. You've raised your pressure. By the same token, if you have winds blowing apart aloft, what happens? The air below it's going to want to rise. You've lowered the pressure. We've just talked about how a low pressure can be formed. The ideal gas law is a relationship relates pressure, temperature, and density. If I know two of the three, I can calculate the other one. So, because air is cooling when it expands, the temperature of that gas drops. All right, I like the bike tire example, or if I was putting air in my car tires and released them, boy, that air coming out gets very cold very quickly. By the same token, if I'm pumping up, it gets hotter. So if you're compressing the air together, if you're using energy, you're heating the air. If you're pushing them apart, you're cooling the air. So if an air molecule, or air parcel of air, we'll describe an air parcel, whatever you want to imagine it. I'm going to say 100 meters by 100 meters by 100 meters. Pick that section of air. If I raise that parcel of air up, the air within it is going to expand, cover more area. It's going to be cooling. If I push that same 100 meter down, it's going to be pushed together. It's going to be warming. And here you can see that. With that, we can actually calculate how the temperature should change with height if the air is dry. Notice I said dry. There's a factor that's going to weigh in here, and we talked about that last week some with moisture, a little bit with temperature and latent heat, but we'll get into that some more. So as you go up in a dry air mass, the temperature actually is going to cool about 5.5 degrees per 1,000 feet. So if I'm hiking up a mountain or driving up into the mountains, I start out at 1,000 feet, I rise up to 3,000 feet. That temperature should have cooled about 11 degrees. And it probably will have, because it's very dry air mass if it's that way that day. So remember that when you're hiking up or down mountains. Now, if I went down, I've just warmed 11 degrees. Now, moisture, because of latent heat, changes the whole equation here. So instead of being that temperature change at that rate, once you have condensation, heat is released, and immediately the temperature is not going to cool as fast. So when you have moisture where the temperature is saturated and the air is completely saturated, you wind up not cooling as fast. So let's go out of this for a second. I wanted to show you a meteogram because you're going to see them this week. This is green is relative humidity. The dark purple blue is dew point, and the other one is temperature. So you can see how they're squiggling all over the place. They're just plotted with time. So the relative humidities are going to be very high or close together. High relative humidity when dew point and temperature are close together. So if I wanted to look, say, at this over sea level pressure, and this is, I think, Newark. Yeah. So you can see here sea level pressure has been dropping at Newark since the 23rd. This is the 24th. It just kind of fluctuates around. Now we have low pressure beginning to approach us, and the pressure has been continuing to drop down here. As that low pressure is getting nearer from the west, it's actually dropping faster. So you can see how pressure is changing as these air pressure systems move toward us. And you can actually see that looking at this week's map. This is getting closer. The front is approaching you. Pressure is dropping. And finally, I can even look at it on Storm Prediction Center and see it in. An interesting fact here, we talked about convergence. I wanted to, of air aloft. If the air is being pushed down, which happens out in front of a thunderstorm, the pressure actually rises there. So that is what you can actually see what we were talking about, that convergence pushing air down. So hope you got a little bit out of pressure this week. Let me know if you have any questions.